Hi, this video lesson is for Chapter 1, Section 1, Graphs of Equations. Please turn to the page 70 in your textbook. Get out your notebook and we'll get this one started. First thing, we have a vocab word here, graphs of equations. Graphs of equations are sets of all the points that are solutions to the equation. Many times we see this one represented with a picture. We're actually looking at a graph on graph paper. Other times it's maybe listed for us in a table of values. Okay, but graphs of equations are going to have many, many points, an infinite number in a lot of cases. So sometimes the picture is the only way to sum that up. Checking to see whether a given point is a solution to an equation. We're going to take the given point, the given xy, we'll fit it into the equation and we'll solve. True statements are going to mean that the point is a solution. False statements will mean that it is not. So let's do an example of that together here. In the example, it's asking us, is 2, -1 a solution to the equation y equals 3x minus 7? All right, so we plug in our x value of 2 and our y value of -1 and we check it. So -1 is equal to 3 times 2 minus 7. All right, so you can see I've just put those two values into the equation that was given. Start solving. So the next line would read -1 is equal to 6 minus 7, or -1 equals -1. It's a true statement, so the point 2, -1 is in fact a solution. If we'd gotten something that would have said maybe -1 is equal to 4, that's false. It would not have been. One way of graphing is the point plotting method. Some folks call that making a table of values. So you get to pick. Okay, pick several x values, plug them in, and find y's to go with. Make that xy table and then graph it onto graph paper. Turning your book to example number 2 in the text on 71. All right, the example 2 there for you is finished in the book. We're actually going to do one together that's not in the book. It's at the very bottom of the page in the checkpoint section. With most of our lessons, I'm going to use those checkpoint ones because the other example is done. You can see that one already. This way it'll provide you with a couple of examples. All right, so sketching the graph of y is equal to -3x plus 2. Hopefully you can see that at the bottom of the page there. That's the one that we're going to do. In your table of values, it's suggested that you pick at least 3 points. 5 is maybe better. And you might want to consider a mixture of positives and negatives in there. Okay, so these are the points that I'm going to pick. Okay, and if we plug those into y is equal to -3x plus 2, my first value I chose was -2. Which turns out to be 8. So there's 1 point for my graph. My next one I chose was an x value of 0. I'm going to plug that in next and solve. Get a y value of 2. And I'm also going to do another one. I picked x was equal to 2, so I'm going to plug that in next. -6 plus 2, or -4. So once you have those points to plot them. -2, 8, 0, 2, 2, -4. And there's our graph. Okay. All other points that would fall on that line or lie on that line would also be solutions to that equation. Find example number 3 now on page 72. Some of the graphs that we look at, or some of the equations that we look at, are actually quadratics. You will be able to identify them because they're going to have an x squared term in them. These kinds of graphs end up being the parabolas. Remember the ones that end up curving up like this? They have a symmetry to them. They don't have to go up and down. They could end up going left or right as well. But those are all generated when you have a squared term in the equation. Okay, the ups and downs come from x squareds, and the left and right ones come from quadratics that have a y squared. Okay, regardless, these are a real common kind of equation that we graph as well. Now, coming up with your table of values with these is a little bit trickier, not in that it's hard, but you want to have a starting spot. We want to be able to find the vertex of our parabola. So in other words, we want to find this spot and this spot because it's kind of the starting spot. It's that maximum or minimum of our parabola. And without knowing that exact point, we can't find those symmetrical sides. We don't know what other numbers to pick to find that curve. So on my slide here, this statement, negative b over 2a, is going to help you find the first x value that you want for your table. All right, I don't remember for sure. I don't think that I found that in the text itself, so make sure that you have that part written down. I think it's probably familiar to you or you remember it from the past, but negative b over 2a is going to give us our first or our starting x value for our graph. Let's do one together here. Okay, now what did I mean by the b and the a in that negative b over 2a? Remember your quadratics all come of the form ax squared plus bx plus c. Okay, so in this particular quadratic that we do not have a middle x term. All right, so for this particular problem, a, which is the coefficient of x squared, is 1. B must be 0 because there is no middle term here. And then C is equal to 3. All right, so using that information, I'm going to find that first vertex point for my table. Negative b over 2a is going to end up being 0 over 2 times 1, which is 0. So I can start my table of values. I want 0. Now, this is going to be one of those parabolas. If the vertex is 0, that means the other values are going to surround 0. So I'm going to choose numbers that surround 0. Negative 1 and positive 1 should mirror each other. Negative 2 and positive 2 should mirror each other. Okay, so let's find out our values at those points. So y is equal to x squared plus 3 is our equation. Put my first value of x in, and I'm going to solve and find 3. Next one, I want to put in a negative 1 for x. Square it. Negative 1 times negative 1 is 1. 1 plus 3, I get a value of 4. My next value is a positive 1. Put that in. Notice when you square a positive 1, you're going to get the same thing as when you squared a negative 1. So I'm going to get an identical y value for those 2 points. That's what creates that symmetry or that curve for our parabola. Put in 2. We end up with 4 plus 3 or 7. Put in a positive 2. Oop, that was, I guess I did the positive 2 already. I'll do the negative 2. And I get another 7. So I have a little out of order there, but for the negative 2 and the positive 2, you're going to get that positive 7 value. Now I can make my graph. 0, 3 was a point. Negative 1, 4. Positive 1, 4. Negative 2, 7. Positive 2, 7. And you can see how that curve for our parabola is made. Symmetrical along the y. Intercepts. Intercepts are another common term that we have in our algebra. When we're talking about intercepts with graphs, we're looking for where are the intersections between our graph and the axes that are on our coordinate plane. Okay, so we have y-intercepts, we also have x-intercepts. X-intercepts are going to be used for many things. Part of it's for graphing, of course. Otherwise, they're also considered solutions to our equations. We're looking for values where y is equal to 0, and those x-intercepts all will be. Okay, y-intercepts, of course, we remember, hopefully, and we will get to that here in a couple of sections. Those are used with that one form of graphing lines when we're doing slope-intercept form. Turn to page 73. Okay, let's identify some intercepts off the examples that are there. Okay, if we're looking at the actual example number 4 from the book, find the intersection points on the x-axis and y-axis. Let's do the x-axis first. Can all of you see that there is an x-intercept at -1, 0? Okay. That graph also crosses the y-axis up at 0, 1. Okay. Drop to the very bottom of the page. I did not redraw these pictures. You guys are just going to be hopefully following along in your book with me right now. Take a look at the parabola that's at the bottom of page 73. Identify the y-intercepts first. Okay, so I'm going to, on the board here now, while you're watching, write down a couple things. Oops, y-intercept. So we're at least all looking at the right answers here. Looking at that graph, where does that curve, where does that parabola cross the y-axis? Okay, hopefully everybody sees that it's there at the origin. It's going to cross the y-axis. X-intercepts, there's 2 of them. All right, so identify the coordinates where it's crossing the x-axis. It also crosses the x-axis at the origin, as well as at the point, what is that, -5, 0? So there are 2 x-intercepts. Symmetry I mentioned already when we were graphing these parabolas. Symmetry is when a figure can be divided in half and each half lines up perfectly with the other. When we're looking at those x-squared equations or those y-squared equations, we should be anticipating that we're going to get that symmetrical curve. If you don't, you're doing something wrong. It's time to go back and reinvestigate. All right, another topic that we're going to deal with in section 1 here are circles. All right, you may recall this equation from the past. Standard form of the circle is x minus h squared plus y minus k squared is equal to r squared. H and k stand for the center of our circle, so those numbers that are in our equations tell us where the center of our circle is. And r, of course, is, as you might guess, the radius of our circle. Notice that in the standard form, that is an r squared, so we would have to take the square root of that or unsquared to find the actual radius itself. Be on page 76 with me now. Okay, we're going to do one of these problems together and play around with that standard form of a circle. Again, there's one done for you in your book. We are going to do another one. We're going to do the checkpoint that's at the very bottom of the page again. All right, so that checkpoint tells us that the center of our circle is at -3, -5, and a point on the circle is 1, -2. So the center is very important to us. That represents our h and our k. Okay, so right here we have the numbers that we're going to use for h and k in that standard form of equation. Now, what does the point on the circle help us with? Well, we needed a radius. If we have the center and we have a point on the circle, the distance from the center to that point 1, -2 is going to be a radius. Okay, think about that for a second. If you have your center and you have a point on the circle, the distance between them makes a radius, right? All right, so we're going to dig deep here and we're going to think back to our distance formula from Algebra 2. Okay, the distance formula was this if you don't remember. Okay, so that there is going to help us find that radius. Let's start with that. Okay, x sub 2 is -5. Whoop, that's y, sorry, back up. Well, let's do that again. X sub 2 is -3, which means that x sub 2 just simply means the x value of the second point. And we want to subtract the first x, which is a 1, and we want to square it. The y value, y sub 2 is -5, and we want to subtract a -2. Now, careful with that. You are subtracting a -2. Remember what subtract a negative does? It becomes plus. Okay, so -3 minus -1 is a -4. And again, we're going to be squaring that in a second. -5 plus 2 is -3. And we will be squaring that. So we end up with the square root of 16 plus 9, which is the square root of 25, which is actually a nice one. So that distance between those 2 points is 5, so that means our radius is 5. All right, now we have everything that we need in order to come up with that equation of our circle. So remember from our previous slide, we're looking to fill in this thing. Okay, h again was a -3. X minus h then is going to be x plus 3. Y minus k. K is -5. So y minus a -5 will be y plus 5. Our radius we just found was 5. Square it, and we get 25. So that would be the standard form of this equation of a circle. Right there. All right, here comes your assignment. 5 problems that I'd like you to give a try to and hand to me tomorrow. That does not mean to practice only these 5 problems. Okay, but get a start on it. We'll go over a bunch more in class together as a group. So start with that, and we will go from there.